Hi, today we're going to be looking at, um, so we've been looking at weak acids titrating with strong bases, and we have this titration curve. And if you recall, this region here, this whole region is we have a buffer. So a buffer, just remember, is when you have a weak acid and its conjugate base both in solution, both things can interact with an acid. So the conjugate base can interact with an acid if it's added, or the weak acid can interact with a base if that's added, and that can buffer the effects of whatever acid or base is being added. So if you just have water and you just add an acid, it's going to make it really acidic. Or if you have water and you have a base, and you add it, it's going to make it really basic. A buffer can counteract those effects. However, um, and so we want buffers. Sometimes we just want to make a buffer. So, for instance, if you're doing a lab for biology or where you're using enzymes, and those things need a specific pH range to react in, you want to make something that is going to be a certain pH, so it's not going to change a whole lot if you have some kind of reaction. Your blood's a buffer. You don't want that pH to change a whole lot, and you don't want to titrate to get to that buffer. So we could titrate and say, oh, I want to get to this buffer range, but instead we just add something else to it to make it a buffer. So you make the solution, you can add something else, and now we have a buffer. So the first thing I want to talk about is, well, how do you pick what type of acid you use for a buffer? So the rule of thumb is if you have some acids, this is pH, so this is acetic acid, for instance. Acetic acid has a Ka of 1.8 times 10 to the minus 5. You can have other acids. I don't have any off the top of my head right now, but if I want a buffer using this, what buffer range am I gonna, what pH range am I gonna look at? And so the rule of thumb is whatever your buffer is, so the buffer range, you want the pKa to be about the same as the pH of the buffer. Okay, so just ignore the phone. I'm going to let it ring. I want to take the negative log of this. So if I'm going to take the negative log of this number here, 1.8, so negative log of 1.8 times 10 to the minus 5, that is, so this is going to be 4.74. That's going to be around the pH range of my buffer. Okay, let's say I had a different acid. If I had a different acid, and that's the Ka of that is, let's say 3.0 times 10 to the minus 6. So what would that give you? So you take the negative log of this, 3 times 10 to the minus 6, and you get pH would be 5.5. And so that would be a little higher buffer. That's how you pick a buffer. Okay, so that's kind of the rule of thumb. I'm just going to erase all this stuff here and start looking at a problem in which we make a buffer. So I have this buffer. It's going to be somewhere around 4.7. I want to make this in the buffer range of that. And the way I'm going to do that is if I have, if I'm adding stuff, I want it to be somewhere near this range here. Remember here I have all acid, so HA. Here at the equivalence point, I have all A negative and water. And in the middle somewhere, I have both. And what we're going to do is we're going to start with the acid and just add the conjugate as a solid. And the solid is going to be in the form of a salt. So it's going to be the conjugate base plus usually sodium or potassium. that's going to be the solid we're going to add. So here's the problem. Suppose I have 150 milliliters of 0.2 molar acetic acid. And this is the formula for acetic acid. If I have 0.025 moles of solid sodium acetate, so sodium acetate has the formula Na, so usually we write CH3COO Na. So this is the acetate ion, this is sodium. If I add solid amount of that, what would the resulting pH be? Assume volume change is negligible, so we're not going to change the volume of the solution. The K of acetic acid is 1.8 times 10 to the minus 5. So let me show you how to do a problem like this. We're going to start off, and we are not going to titrate anything, but we do have something in equilibrium, so we're going to set up a Rice chart. Okay, so I'm going to move over to this side of the board here. So I have a Rice chart here, that's CH3COOH. It's going to be in solution with H plus and CH3COO negative. And my initial concentration is 0.20 molar. Okay. Normally, I would have zeros on this side here for regular acid. Zeros on that side. However, I am now adding this ion, and so I can't say that is I can no longer say that that's 0. And so we're going to have 0 here, but we're going to have something in this box here, and that something is going to be the molarity of the acetate ion. So to calculate the acetate ion concentration, we have 0.025 moles of acetate. And that's from the problem statement, and we're going to divide it by the volume. So the volume is 0.150 liters, and if we do that math, 0.025 divided by 0.15, that's going to be 0.167 molar. Okay, that's going to go here. So 0.167 molar. Now, we have two things, and so that's my buffer. That's my definition of a buffer. I just made a buffer. I just took some solid, added to it. I'm going to put my x's here, so plus x, and then now I'm going to go 0.2 minus x plus just x, and 0.167 plus x. I want to find the pH of this, which means I need to find x. Okay, so H plus concentration, I need to get that, and then eventually get to X. And the way that I do that is, these are all set up, connected by Ka. So I'm going to write the Ka expression. Ka is H plus, CH3COO negative, all over CH3COOH. And then I'm going to plug in these things here. So I have X times 0.167 plus x all over 0.20 minus x. And that's all equal to 1.8 times 10 to the minus 5. Now, if you look at this here, this is some terrible math. I would have to do a lot of awful algebra to get to that answer. However, if you recall, X is really small compared to the molarity. And because this is minus X and this is plus X, these numbers here are going to be dominant over this little x. So what we can do is, with this minus X and this plus X, we can assume that they're small. Both of them. This X I can't get rid of because it's multiplied. That's a different effect. But now I have this number here. So I have a ratio, I have an X, and I can go ahead and just solve for X. Okay? So this number here, I can take that. If I just divide it out, 167 divided by 0.2, that's 0.835. So this is X times 0.835 equals 1.8 times 10 to the minus 5. Okay, divide both sides. I'm going to divide both sides by 0.835. And now I can solve for what x is. So 1.8, I have my fancy, use this function here, alpha f1, and I got 1.8 times 10 to the minus 5 all over 0.835, and that is 2.16 times 10 to the minus 5. Over here, x equals 2.16 times 10 to the minus 5. That's in molarity, because this is your H plus concentration. And then now I can get the pH. Just take the negative log of that, negative log, answer, just like that. And then you get 4. X is 4, sorry, pH 4.67. Okay, so that is how to solve for the pH of a buffer if you're adding a solid to that.